Have you ever wondered how electronic circuits manage to maintain a perfectly steady voltage, even when the current demand fluctuates significantly? It is a critical function in many applications, and one key component in achieving this stability is the Zener diode. The Zener diode's dynamic impedance, often denoted as ZZ, is fundamentally determined by the slope of its reverse bias current voltage characteristic curve within the Zener breakdown region. Essentially, it represents how much the voltage across the diode changes for a small change in the current flowing through it when it is operating in its reverse breakdown state. The why behind this determination lies in the unique breakdown mechanisms within the Zener diode. When reverse biased beyond a certain point, the diode enters either Zener breakdown or avalanche breakdown, depending on the doping and junction width. In both cases, the diode exhibits a remarkable property. It allows a significant increase in current with only a very small corresponding increase in voltage. This nearly vertical segment of the IV curve signifies a very low dynamic impedance, which is precisely what makes Zener diodes excellent voltage regulators. The higher the doping concentration and the thinner the depletion region, generally the sharper the breakdown and the lower the dynamic impedance. In practice, you can determine ZZ by taking two distinct operating points on the Zener diode's reverse IV curve in the breakdown region. Calculate the change in Zener voltage, often written as delta VZ, and divide it by the corresponding change in Zener current, or delta is. This ratio, delta VZ over delta is, gives you the dynamic impedance at that specific operating region. Alternatively, for many commercial Zener diodes, the dynamic impedance at a specified Zener test current is conveniently provided in the device datasheet. It is important to understand that Zener dynamic impedance is a small signal resistance, meaning it applies to small AC variations around a DC operating point, differentiating it from the static resistance, which would be the total voltage divided by the total current. Furthermore, this dynamic impedance is not perfectly constant. It varies slightly with the operating current and can also be influenced by temperature changes. Manufacturers often specify ZZ at a nominal Zener current. Ultimately, a low dynamic impedance is the hallmark of an effective Zener voltage regulator, ensuring that the output voltage remains remarkably stable despite significant fluctuations in the load current or input voltage. This inherent characteristic makes Zener diodes invaluable for providing reliable reference voltages and protecting sensitive components in countless electronic designs.